To welcome everybody to research session 25, temporal and spatial data. And this is the third session of this track. And it is also one of the last sessions of the technical program. I thank everybody for sticking around until the very end. We have 4 excellent papers focusing on spatial temporal data in this session. As you will see, the papers tackle a diverse set of problems, and they are applying spatial temporal data and solving these spatial temporal data challenges in wide range of applications, from recommender systems to indoor tracking. So each paper will have, like the other tracks, each paper will have 15 minutes of presentation. And we will basically try to allocate 2 or 3 minutes for Q&A. As always, we'll first play the videos, and then I will open the floor for questions. In the meanwhile, please feel free to use both the chat window or the Slack channel for your questions. I actually encourage you to do so, so that we can have as interactive a session as possible. So with that, let's go to the first presentation. The first presentation of the session, the title of the paper is called Sequence-Aware Factorization Machines for Temporal Predictive Analytics. The authors are from University of Queensland, Griffith University, and National Chiao Tung University. The presenter is Tong Chen. He's a PhD candidate at University of Queensland. I believe it's his final year at the university. His research interests include data mining, machine learning, and artificial intelligence. More specifically, he's conducting research on sequential recommender systems, user behavior modeling, and commercial time series analytics. And this talk today is on sequential recommender systems. Tong, I think we'll basically go ahead and start your presentation.
Everyone, I hope you are having a fantastic day. I'm Tong Chen, the presenter and the first author of this paper, and I'm from the University of Queensland, Australia. The work I'm going to present today is called Sequence-Aware Factorization Machines for Temporal Predictive Analytics. So with that said, let's start now. First, a little overview. The problem we're going to study here is called predictive analytics, and I believe that is a familiar name for most of you. It has a wide variety of applications, including the rating prediction in recommender systems, the stock price prediction in financial analysis, and also the click-through rate prediction in online advertising. Usually, to make predictions, we're going to take the values of some features, like the age of a user or the temperature of a day, and convert them into the feature vectors. And we want to learn some predictive models to map those input feature vectors to the desired prediction results. And we do have some classic and effective models to do so, like the logistic regressions and the support vector machines. But apart from those numerical features I just mentioned, there is another type of features called categorical features. And those traditional methods cannot directly use the categorical information to make predictions. So a common solution would be converting those features into the one-hot encodings. For example, if we have a feature called gender here, and I can simply convert that into a 2-digit one-hot encoding. However, in reality, those one-hot encoding are usually very high-dimensional but very sparse. For example, if you go to any online shopping platforms, you will find millions of different products for you to choose from. But at the end of the day, you're going to only interact with a few of them. So simply using the raw but very sparse features with those traditional methods can hardly give us any optimal results. So the cross features are a kind of feature engineering-based solution to this problem. For example, if we have 2 individual features, the occupation lecturer and the level senior, by combining those two features, we can have a new cross feature called senior lecturer, which obviously can offer more context during the prediction stage and give us more accurate results as well. However, this kind of feature engineering is very labor intensive for many machine learning tasks, and it's very, very impractical. So the factorization machine was proposed 10 years ago to solve this problem by modeling feature interactions via the inner product of their embeddings. So if we want to predict a user's annual income, so we have the features here, the user ID, the gender, the cities visited by this user. I will first have the input vector like this, the x, and I will feed it into the mathematical form of the plain factorization machine. So the basic idea behind the factorization machine is relatively simple. So the orange part is the global bias, and the green part assigns individual feature weights to different features. And the blue part is the core part of the plain factorization machine, which models the pairwise interactions between two different features using their dot products. Of course, these are the embedding, not the raw features. So because the plain FM is so effective and accurate in predictive analytics, we have witnessed some popular linear extensions to the plain FM after it has been proposed. For example, we have the high-order factorization machines, and it extends this blue part here by adding more features to create higher-order feature interactions. Also, we have the field-aware factorization machines, and this model has already proved itself by winning 2 Kaggle data challenges related to click-through rate prediction tasks. So in the recent years, we have seen the prominent development of deep learning techniques. So naturally, improving the performance of FM-based models with neural networks has become a very, very popular research direction. And I have just summarized the 2 major trends in the current development of FM-based models. The first one is obviously going deep with multi-layer networks. So let's take this neural factorization machine as an example. So on top of the linear interaction layer, the authors stack multiple hidden layers upon it, and this gives better prediction results eventually. And the second approach would be going wide instead of going deep by combining multiple feature interactions from varied domains or contexts. And we have an example called wide and deep model here, and it has a linear model and also have a non-linear model consists of the neural networks. And in the output layer, it combines the interaction results from 2 components, and this provides more context and more accurate results in return. However, as we go along this line of research, we have found that in many real-life prediction applications, we're actually taking a step up because the raw features may contain valuable temporal information. And this brings us some unsolved challenges by existing FM-based models. So first, these models are mostly developed for non-sequential predictive analytics, and this can be verified by their experimental settings. Second, these models still lack the consideration of sequential dependencies when modeling high-order feature interactions. So this gives us the opportunity to investigate an important research question, which is how can we actually combine the feature interaction scheme with sequence awareness in FM-based models? So with this motivation, we have proposed our own sequence-aware factorization machine, or what we call the SeqFM in short. And to give you a better idea of how SeqFM works, I'm going to present an intuitive example here, which is a general sequential recommendation scenario. So we have a user here and his purchase sequence as the features, and we're going to predict whether the user is going to purchase the keyboard or the belt at his next move. So for the traditional FM-based models, because it can only model the interactions among different features from a static point of time, it cannot distinguish the importance of the close or the electronic devices to the user. So it cannot distinguish the current interest of this user, whether is that on the keyboard or the belt. However, our proposed SeqFM models the feature interactions from 3 distinct views. So we have a static view for static features, we have a dynamic view for dynamic features, and we also use a cross view to model the interactions between a static feature and a dynamic feature. So here, to give you some more details of about the SeqFM model, we have printed the workflow of the SeqFM model here on the left. First, we need to get 2 input matrices consisting of the 1/2 encodings of the static feature and dynamic feature. And we also have the real examples in the scenario of sequential recommendation here. We use 3 different notations to mark the parameters from 3 different views as well. So after the embedding layer, we have 3 self-attention units in 3 different views, and we have 2 different attention masks in the cross view and the dynamic view. After that, we will do an intra-view pooling, which is essentially an average pooling operation. And we stack a shared residual feed-forward neural network upon the pooling operation layer. And at the end, we're gonna combine the information from 3 different views and do a linear projection to get the final prediction result. So because the 2 attention masks in the dynamic view and the cross view are the key components to ensure smooth feature interactions in our proposed model, here we use a bit of extra time to explain the rationale of them. Essentially, the 2 attention masks are used to block unnecessary feature interactions in different views. So here, we take our dynamic view as an example, and suppose we have a feature sequence of 4 different items, and each A represents an interaction score between 2 items. So in common sense, when item 1 first appears, it won't be having any chance to interact with any of the following items, which are item 2, 3, and 4. So by applying an attention mask like this, we can block those unwanted or irrational item interactions in the corresponding positions. And with the effect of the softmax function, we can generate the attention weights, and with the unwanted positions having the value approximate to 0. And by this means, we can make our SeqFM preserve some nice features as the recurrent neural networks. And eventually, we have applied our model to 3 typical tasks in recommendation settings. Firstly, the ranking task, which is the next point of interest recommendation. We have optimized our model using the BPR loss. And for classification task, which is the click-through rate prediction, we optimize SeqFM using the log loss. And lastly, for the regression task, which is rating prediction, we use squared loss as the loss function. So it's now time to validate the performance of our proposed model. And specifically for each type of the task, we use two different large-scale datasets for evaluation. And apart from the general baselines we have chosen, for each specific task, we have chosen two state-of-the-art methods as two additional baselines. And as we can see from the results, our proposed method has significantly and consistently outperformed the chosen baselines. Also, we have conducted some parameter sensitivity analysis regarding the performance affected by the dimension D, the layer number L, the sequence length N, and also the dropout ratio rho. Furthermore, we have conducted ablation study to verify the contributions from different model components and also the training efficiency, which is done on the largest dataset, which is the Trivago dataset. So, time to wrap up the conclusions. So, in this work, we have made three contributions. So, the first is to point out that mining features sequential dependence in FM-based models is actually beneficial. The second is that we have proposed a novel method called SeqFM. The third would be evaluating SeqFM by comparing
Hello. Yeah, Tom, thank you so much for the very clear presentation. I lost the very end of the presentation though. Kushagra, was that on my side or were you?
No, we also lost it.
All right. Okay. So I was worried that it was on my side. Okay, great. Thank you so much. So Tom, again, thanks a lot for the very clear presentation. Very interesting work. And I think we can open the floor for questions right now. I would like to ask the audience to unmute themselves and ask their questions. I think there's a question from Maolin Lee. Maolin, do you want to unmute yourself and ask your question yourself?
Oh, hi. Thanks for the presentation. So I did very good presentation. So I have a question about your attention max. Is that current, as we see in the presentation, your attention max can focus on the significant interaction, and it looked like to me it's kind of a two feature interaction. So do you think it's possible to extend this mask scenario to a higher order, like the interaction within 3, or even more feature interaction for the attention max?
Yeah, so first, thanks for your question. I think due to the effect of self-attention, so in the dynamic view or in the static view, once we do the kind of self-attention for each position in the queue, or what do we call each individual feature, we are actually doing a kind of weighted sum according to the importance of different other features to this particular one we are looking at. So essentially, at the last operation of the self-attention, we are aggregating the impact from different other features to form the new representation for the current feature we are looking at. So it is essentially a kind of high order interaction because it combines all different features by taking their weighted sum.
Okay, I see.
Okay, great. Thanks a lot for the question, Maolin, and thanks a lot for the answer, Tom. I think there's another question on the chat window from Michael Boland. Michael, would you like to go ahead, unmute yourself and ask your question?
Well, I can try. You'll hear me?
Yes, we can hear you.
Yeah.
Okay. So my question is simple. So instead of you describe this blocking of impossible sequences, so do you also consider some form of decay, time decay, and what do you expect to happen?
So this is actually a part of our next work. So the design of time decay, in our view, could be a bit data-driven or case-specific, because different kinds of data may be suited to different kinds of decaying functions. So in this work, we primarily ensure the sequential associations in the dynamic view using a kind of attention mask to block unnecessary ones. And yeah, that is currently how we do it. But your suggestion is definitely a very good idea.
So Tang, I have also a very quick question. So you, obviously factorization machines, as you correctly point out, right, have shown great promise in recommendation systems. But there are also other techniques, right? So such as dynamic collaborative topic models, which are inherently sequential, right? So there is tensor factorization techniques like DEDICOM and so on, which are again inherently sequential, inherently time aware, right? Can you basically contextualize your work within the context of these other type of approaches to time aware sequential recommendations? Maybe you have not compared your work against them, for example, right? So what will be the advantages of, for example, using a sequential factorization machine as you propose against using a dynamic collaborative topic model, which is basically doing prediction in a different approach, using a different approach.
Yeah. So for sequential recommendations, there are definitely a lot of variants of solutions to the same kind of problem. So I think the advantage of the factorization machine-based models are because they take the features explicitly and make them interact with each other explicitly. So we are able to explain how the desired results is produced by explicitly arranging the feature interactions. So that gives us a bit of good interpretability.
Perfect.
In terms of explaining the result we have got in the recommendation setting. Yeah.
Perfect. Yeah. Thanks so much. Thanks a lot, Tang, for your very clear answers as well. Thank you again.
Thank you.
Let's go to the second presentation of the session. The second talk, the title is Stochastic Origin Destination Matrix Forecasting using dual stage GraphConvolutional and Recurrent neural networks. The authors are from the Inception Institute of Artificial Intelligence, Aalborg University, and State University of New Jersey. The presenter is Jilin Hu. Jilin is a tenure track assistant professor at Aalborg University. And before joining Aalborg, he was a research fellow at the Inception Institute, where I believe the research was partly done. He received his PhD degree also from Aalborg University in 2019. And his research interest obviously includes spatial-temporal data management, with emphasis on traffic data analysis and machine learning. So once again, we'll play the video and then we'll ask Jilin to answer questions. Let's go ahead and start the presentation.
Good afternoon, everyone. My name is Jilin. This is the first of this paper. Today, I'm going to introduce our paper for stochastic origin destination matrix forecasting using dual-stage GraphConvolutional recurrent neural networks. This work is co-authored with Bin Yang, Chen Juanguo, Christian Jensen, and Hui Xiong. And this work is conducted in Aalborg University, Denmark. So what is OD matrices? OD matrix in transportation processes, it is important to understand the costs of travel between zones. So the OD matrices is, so for example, here we have a map with the district of the New York City, and this is the Manhattan district in NYC. So, and in this district, we can separate it into 67 regions. So thus, we can construct a OD matrix with 67 by 67, and each cell which represents the travel cost within this travel between these zones. So, for example, that this is from zone 1 to zone 1 is travel within these zones. So, what's the travel cost? So, what is OD matrices? So, one OD matrix is per time bucket, and which each cell including the travel costs, which can be speed, travel speed, or greenhouse gas emission, and the time bucket can be 50 minutes, day, or week. So this is the OD matrices we introduced before, and the calculation we can do the Mij at time t, which with aggregation function for all the trajectories at time t. So Tij represents the travel cost from all trips from I to j at time t, and the ATG function means the aggregation travel cost aggregation function, which can be the mean value, the sum, or the trajectories, or the histograms. So, for example, that at element I and I to j, ij, so we have this travel speed distribution, which with 10 to 20 kilometers per hour, it has 0.5 probability. 20 to 30 kilometers per hour, it has 0.3 kilometers per 0.3 probability, and with probability 0.2 from 30 to 40 kilometers per hour. And then if we have two regions, I and J, and there are 2 points within this route, and then we want to go from this point to this point, and the shortest path is 15 kilometers. Thus, according to this distance and the travel speed, we can get the travel time distribution with these properties, which is just to the time divided the speed upon and low bound. Then we get this travel property. Thus, that we can know that better that how can we ensure the user can reach the destination on time. So stochastic OD matrices, we just can, here is a runner level, we can separate it into 8 regions, and then we can do a OD matrix with a tensor, because in each cell, it may contain several different values for the different buckets. So here, here is a region, here destination region, and this dimension represents the different speed buckets. So this is OD matrix tensor M, and this is the adjacency matrix, which to represent that the adjacency relationship between regions. So here, for example, here the first line, that the region 1 is connected to itself, it's connected to region 2, and it's connected to region 4, and it's connected to region 6. So when related to this figure here, we know that 1 is related to 2, and 1 is related to 6 and 4. So it has this addition matrix. So it means that actually at either a region dimension, or in the destination dimension, those regions, the relationship among those regions follows this addition matrix. which can be regarded as a graph signal. So our problem statement is to OD matrix forecasting. So this is our historical sparse OD matrices, and we want to have this historical observations. We want to forecast the future for OD matrices. And for each OD matrix, sparse matrix, we have this representation. This is sparse because not all the region to region have data covered by the trajectories, and this sparseness is quite common in the transportation data. And here is a distribution for example, here is from region 8 to region 7, then it has a distribution with 0.3 probably to 10 to 20, 0.5 probably 20 to 30, and 0.2 probably for 30 to 40 km/h with for speed. And this question symbol is for the cell that had no observed data. And so this is our problem for our formulated problem, which has a historical observation time intervals when to forecast the future time intervals. As a framework, we can regard as this. So we have the historical sparse OD matrices. Then we do factorization. We make these sparse OD matrices into low rank 2 tensors with R and C, and for each time slot, it has two separate tensors, and then we do forecasting for each low rank tensors separately. So here for C, we can do the forecasting, and for R, we can also do the forecasting. And then after we have the forecasted results of C and R, so we can do the recovery. So for C and R, we can recover back to the M, T+1 and to T+H. So it can be the future forecasting results. And in this slide, I will talk about how do we do factorization in our paper for the advanced method. So here that this is a tensor which is n by n prime. This n by n and n prime can be the same or can be different. Just to see, n is the origin destination, regions, and the n prime is the destination regions, and the k is the dimension for the the length of stochastic weights. So we can do slicing. First, we slicing every this rowly, so we can have n a total number of n with matrix n prime by k. Then we do for each matrix we can do we can slice again such that each vector is kind of graph signal, so it can be joined with origin matrix in the destination dimension. So we have this graph convolution to do graph filtering, and then we have this Q filter results. Then we can do the pooling, so we can condense. So we can condense pooling over the destination dimension. So we can do the pooling, which can be converted from n prime to beta prime, and then we can do concatenation again, so it can become k by beta prime. And this process is kind of encoding process, which is from k by n prime to k by beta prime. So we still, for each one, we can get one, and we can still have n, a total number of n k by beta prime vector matrix, and then we can concatenate them again. So along this dimension, so we can have this n by beta prime by k tensor. So this is kind of factorization, which actually just to do the encoding within the destination dimension. Similarly, we can do the factorization along this origin destination, so we can get the similar operations for C. So for factor forecasting, we are doing temporal. We want to capture the temporal dynamics. So we are using gated recurrent units. So in order to consider about the spatial correlations, we also included the GraphConvolutional network into the gated recurrent units. So this is the formulas. We have 4 gates for the reset gates, update gate, state gate, and the output gate. So in all the reset gate, update gate, and state gate, the GraphConvolution is involved to capture the spatial correlations. And this symbol is for the GraphConvolution, and this is for the Hammond product. So for recovery, it's simple that we just do the matrix factorization with C R hat multiply C hat, and we can get the MT plus J for this time interval for the forecasting. And for the loss function, that we have 3 items. The first 2 is for the regularizer for the R and C, this encoded features or factors, and then this is for the ground truth, which M is the ground truth, and M hat is for the forecasting results, and omega is an indication function to indicate which cell has data or not, has ground truth observation or not. So this is a loss function we constructed, and our framework is trained by backpropagation, which is used in deep learning, and to train these models. So the setup that we have 2 datasets, NYC and Chengdu, and for this, this is the statics about 2 datasets, and this is 2 regions that we visualize here. And for the NYC, that we are using a text zone separation, which is in the dataset, and this is manually drawn by ourselves according to the geo information. So we separate them into different regions. And the baseline where we have the naive histograms, support vector regressor, vector autoregressor, a Gaussian process regressor, recurrent neural network, and multitask representation learning MR. And for the evaluation matrices, that we are using the dissimilarity measure to measure how dissimilar the ground truth and the forecasting results. And then we're using, for the matrix, we can using the KL divergency, for the Jensen-Shandong divergency, and also for the EMD distance. So this is the formula for the dissimilarity measurements. And then we have the results, which will show that the forecasting results with varying horizons with the historical observation 6. So clearly that we can see that our method AF is the state of art compared to other methods, and it has a big margin over other methods. And for the also we illustrated that for the different time of day, the performance on EMD metrics, which we can see that NYC that our advanced method is always the lowest one on the paper compared to other deep learning based method. And also this one is also for CD is also the lowest one below here. And the conclusions and outlooks. Conclusions that we have increasing settlement setting asking for OD matrices, define and study the problem. And also we have empirical studies on two real sets to evaluate the effectiveness. Outlooks, we can extend the framework to incorporate contextual information, consider the information at different time steps, and using attention networks. And it is interesting to explore outlier predictions. Okay, thank you.
Dear Julian, thanks a lot for the great presentation. We have a couple of minutes for questions. So I would like to first give a chance to the audience. If anybody would like to ask a question, you can unmute yourself and go ahead and ask the question, please. Okay, so let me go ahead and ask my question then. Jilin, very good work. It is a very interesting way to actually combine factorization with graph convolution networks to support forecasting. My question was with regard to the factorization step of your approach. As you probably know, there are factorization techniques like Dedicon for tensors which have temporal sort of structures, right? So it has been very successfully used on sparse evolving graphs, for example. So I was wondering whether you thought about, instead of basically using coming up basically with a specific, with your sort of new way of doing the tensor factorization. I was wondering whether you considered using some of the existing sort of dynamic sparse graph factorization techniques like Dedicon.
Okay, thanks. I think this is a very good question. For me, that when I just touch the approach, then we are just considering from the neural network side to consider how can we apply the deep learning on the predictions and for the spatial considerations, because the graph neural network is quite hot in that in this period, and but we did not consider too much about the dynamic graph this consideration, but I think it's quite interesting to look into it maybe for our future works. Yeah.
Okay, yeah, thanks a lot. No, I think basically your the proposed approach is very interesting, but I was sort of wondering what will be the trade-off between this existing techniques and your technique.
Yeah.
That's great. Thanks a lot, Jilin. Any other questions from the audience? Okay, if there are no other questions, let's thank you again, Jilin, and let's go to the next paper, the third paper in the session. The title of the paper is Query Results over Ongoing Databases That Remain Valid as Time Passes By. The authors are Yvonne Muller and Michael Bolen from University of Zurich. The presenter is Yvonne Muller, and she is a PhD student at the University of Zurich, supervised by her co-author, Professor Michael Bolen. Yvonne received her bachelor's degree as a master's degree from Karlsruhe Institute of Technology. And once again, we'll first play the presentation, and then we'll open the floor for questions. Let's start the presentation.
Hello, my name is Yvonne Müller. I'm a PhD student at the University of Zurich, Switzerland, and today I'm going to present you our paper, Query Results over Ongoing Databases That Remain Valid as Time Passes By. So what does ongoing mean? Every one of you is familiar with fixed time points. An example is the 25th of January. Fixed time points have the same value as time passes by. In contrast, ongoing time points change their value as time passes by. To determine the value of an ongoing time point, we use the reference time. As you can see in the left figure over here, fixed time point 25th of January has the same value independent of the reference time. It's always 25th of January. Ongoing time point now, in this figure here, is equal to the reference time. That means at the reference time 25th of January, it is equal to 25th of January, and at 26th of January, it is equal to 26th of January. Ongoing time points are often used as part of the valid time to state that the tuple is valid from the start point onward. An example is an application that deals with software bugs. Prioritized bugs are open from the date of its discovery until a fixed deadline for when it needs to be resolved. For instance, tuple B2 records prioritized bug 501 that is open from the fixed time point 25th 30th of March until 21st of August. A deprioritized bug is open from a fixed date onward, and no fixed deadline for resolving the bug is set. Table B1 records deprioritized bug 500 that is open from 25th of January until now. Its end date is increasing as time passes by until the bug is resolved. The state-of-the-art approach to deal with ongoing time points is to instantiate ongoing time points. Instantiation means that the ongoing time points are replaced with the reference time. The SQL standard contains keywords for ongoing time point now with different granularities. These keywords can be used in queries, but they must be immediately instantiated when the query is evaluated and therefore cannot be stored in relations. Clifford et al. Allows storing now in relations, but their approach always instantiates now when a query is evaluated. The result is only valid at the time of the instantiation and does not remain valid as time passes by. Anselmo et al. Propose an approach that can keep now uninstantiated when the result can be represented with their time domain. Otherwise, they must instantiate now. Predicates that reference now can only be evaluated by instantiating now, and thus queries with predicates do not remain valid as time passes by. Torp et al. Propose a solution for temporal modifications. They show the importance for modifications to remain valid as time passes by, since otherwise incorrect data would be stored in a database. To evaluate queries with predicates on time attributes, now must still be instantiated, and thus the query result does not remain valid. So why is it problematic that query results might not remain valid? A key assumption of database systems is that query results only get outdated when modification statements, that means insert, update, or delete, are applied to the underlying relations. With ongoing time points, which change their value as time passes by, the key assumption does not hold anymore. Instead, query results also get outdated as a result of time passing by. The drawbacks are that materialized views and cached query results must always be recomputed before they can be accessed, and since ongoing time points are instantiated with the current approaches, applications cannot identify ongoing time points in the query results anymore. So let me illustrate this. In this example here, we evaluate a selection query on the bug relation at two different reference times. The ongoing time point that we have here in tuple B1 is not preserved in an instantiated query result, as you can see here. Here, the ongoing time point is replaced with the reference time. This means that since it is replaced, it makes it impossible to distinguish between prioritized and deprioritized bugs in the result. Also, the query results differ between reference time. You see here in the left result, tuple B1 is included, and in the right result, tuple B1 is not there. This is the case because the before predicate evaluates true at reference time 24th of August. Therefore, the tuple is included in the result. And at reference time 25th of August, the predicate evaluates to false, and therefore the tuple is not part of the relation. So how looks is our approach? Our approach ensures that queries are evaluated to results that remain valid as time passes by. This means that we evaluate a query at every possible reference time and ensure that the result at each of the reference times is equal to the result that we get when evaluating the query on an instantiated database. Our approach provides support for various operations, the standard predicates on time points and time intervals, for example, the overlaps predicate, and the logical connectives so that we can formulate arbitrarily complex predicates. Since we want to evaluate queries on a database, our approach also provides a relational algebra. To represent the query results that remain valid, we extend the schema of a relation with a reference time attribute. More about that in a couple of slides. So what is so challenging about evaluating queries to results that remain valid? Let's have a look at predicates. Since ongoing values depend on the reference time, the truth value of predicates depends on the reference time as well. For instance, the predicate 25th of January is less than now is false up to reference time 27th of January, and afterwards it is true. The result is an ongoing Boolean whose truth value depends on the reference time. The last line of the equation is the short notation for an ongoing Boolean. The first value contains the reference time when the Boolean is true, and the second part contains the reference times when the Boolean is false. To avoid redefining every predicate for ongoing time points and time intervals, we identified 4 core operations that allow us to express all other standard predicates with these operations. For the core operations, being the less than predicate for ongoing time points and the 3 logical connectives, we provide ongoing specific definitions. For instance, here you see the illustration of the definition of the less than predicate for ongoing time points. We have to distinguish between 4 cases. The first case is where the predicate is true at all reference times. The second case is where the predicate is true up to a certain reference time and false afterwards. The third case is that the predicate is false up to a reference time and afterwards true. And the last case is that the predicate is false at all reference times. Since predicates can be true at some reference times only, this has an impact on how predicates select tuples. It's not a binary decision anymore, but whether a tuple belongs to the result relation depends on the reference time. In order to represent this, we extend the schema of a relation with a reference time attribute RT. We refer to these relations as ongoing relations. The reference times attribute contains exactly the reference time when a tuple belongs to the relation, and this attribute value is restricted by the predicates in queries. As an example, you see here the result of the selection with the before predicate on our back relation. The before predicate evaluates for true in the input tuple that corresponds to B1 at the reference time between 26th of January and 25th of August. At this reference time, the tuple belongs to the result relation, thus we store this reference time in the RT attribute, of the result. At all other reference time, the predicate is false, and thus the tuple is not part of the relation. Here you see how the result will look like at 3 different reference times. Since 23rd of August and 24th of August are contained in tuple B1's reference time, the tuple belongs to the instantiated relations, and you see also that B1 is part of them. Since 25th of August is not part of the reference time attribute of tuple B1, the tuple is missing, so we only have B2 in the result. We evaluated our approach on 2 real-world datasets, the incumbent and Mozilla bugs, and on various synthetic datasets. We evaluate queries with different predicates, the before predicate and the most widely used overlaps predicate. And as queries, we use a simple selection and a complex join over 3 relations. In the following, we will discuss 2 of our experiments. In this experiment, we evaluate the runtime overhead of our approach compared to approaches that instantiate now. For the overlaps predicate, you see it in the left figure, the runtime of calculating the ongoing result, which only needs to be done once, is already more than amortized once the result is needed for at least 3 different reference times. This is because the instantiation approach needs to recalculate the entire result for every reference time. For the before predicate, in the right figure, we see similar results. In this experiment, we evaluate how many more tuples an ongoing result contains compared to an instantiated result. It is expected that the ongoing result contains more tuples than an instantiated result, since the ongoing result contains the result tuples for all reference times, whereas the instantiated result contains only the tuples at a specific reference time. For reference times close to the current time, so that's the right part of the x-axis. Okay, for closing, the size of the ongoing result is equal to the instantiated result for the overlaps predicate and gets close for the before predicate. So let me summarize. We propose the first approach that evaluates queries without instantiating ongoing time points. To represent the query results, we propose ongoing relations that associate each tuple with a reference time attribute. The attribute contains the reference time when the tuple belongs to the relation and is restricted by predicates. To show that our approach is practically feasible, we implemented it in the Postgres kernel. The empirical evaluation shows that our approach has only a minor performance overhead compared to calculating a query result that is valid only at a certain reference time. As part of our future work, we want to add support for the 3 standard functions for time intervals to our framework, and we want to propose an aggregation operator on ongoing relations. Thank you for your attention.
And thanks a lot, Yvonne, for the presentation. I believe we have time for a few questions. If anybody from the audience would like to ask a question to the speaker, please unmute yourselves and ask your question.
Yeah, this is Chris Clifton from Purdue. I have a question. Have you worked out the interaction of the semantics with updates? For example, on slide 11, you could delete, if you deleted BID 500 on the 24th, it would invalidate the result, but the same delete on the 25th wouldn't update or wouldn't invalidate the result. Have you figured out whether you can take advantage of that or whether that all works with the semantics as you've defined them?
Thank you very much for the question. I haven't looked at modification semantics at all because our goal was first to basically get the selection queries working so that we get results that are independent of when I actually issue the query, which is quite an assumption that databases don't have. So of course that if I'm only interested in results that at a certain time, so for example, I'm only interested in, okay, my database looks like that today and I only need the results today, then I could certainly take advantage of only looking at the result for a certain date and then do incremental changes to my query result, because I know from a database whether the data that is stored in it changes or not. But to answer your question, no, I haven't looked at that because it wasn't there. But thank you.
Right, thanks, Chris, for the question. Any other questions from the audience? Yvonne, I have a quick question, especially since your evaluation was primarily based on the overhead of the, not necessarily the semantic, but the overhead of the extension that you proposed. Have you considered the impact of this extension on the optimization of the queries? You propose a relational algebra, right? You evaluate overhead. What about the optimization? So what are the impact of your extension on the query optimization? You implemented on Postgres, did you need to change the optimizer, or would somebody need to change the optimizer if they want to use this effectively?
Thank you for the question. So what I focused on when I implemented it is that I only change the predicate keywords. So that means like something like overlaps or the logical conjunction. But I made sure that, for example, to evaluate a selection query or a join, I still use all the operators that are implemented in the database system. Mm-hmm. So basically, as long as we don't have something like predicates on the ongoing, on the valid time, for example, we still can use all the optimization techniques that exist for predicates that are specific to the valid time, and which basically means that I can only, I need to restrict an attribute value. Sure. It's a bit of a different type of how we select tuples, and this is something the database system thinks. So currently I don't use any indices or so, and I think it's also not that easy to do, because we have, first of all, we have ranges that we look at. So we could, maybe it would be beneficial to find index mechanisms for the reference time attributes, so we can more efficiently find tuples that we can discard because it cannot be in the result. But apart from that, I think, yes.
All right, okay, thank you so much. Thanks, Yvonne. Thank you for your answer. Do we have any other questions from the audience? Otherwise, Yvonne, thanks a lot again, and we can go to the next paper. So the title of the next paper is Indoor Mobility Semantics Annotation using Coupled Conditional Markov Networks. The authors are from Aalborg University, Monash University, and Zhejiang University. The presenter today is Huan Li, who is a postdoctoral research fellow at Aalborg University. This is the second paper in the session from Aalborg University. Huan received his PhD degree in computer science from Zhejiang, and his research interests obviously include spatial temporal data analytics, specifically mobile pervasive computing. With that, I would like to start the presentation, and we will have, once again, the questions at the very end of the presentation.
Hi, everyone. Glad to have you all here. I'm Huan Li from Aalborg University, and I'm going to present our work, Indoor Mobility Semantics Annotation using coupled conditional Markov networks. So mobility analytics can greatly benefit many applications. With large amount of indoor positioning records, an interesting problem is to semantically understand when, where, what about users. In this work, we studied the annotation of indoor mobility semantics that describe an object mobility event at the semantic region during a time period. Here, a semantic region is a predefined area, and a mobility event is a movement pattern like state or path. Referring to the example, in the left, we have a lot of raw positioning records that are hard to understand. By combining them with the context, we can annotate a sequence of triplets. So for example, here we can see that the tourist has stayed in the snake bars during a certain time interval. So such kind of semantics bring advantages. First is intuitive, enabling semantic-oriented queries and analysis. Second is concise, combined to the original uncertain and redundant records. Third is independent of underlying positioning techniques. Organizing data as semantics benefits applications like behavior, inference, and conversion rate estimation. A general idea is to use a label and merge method to construct the semantics. In particular, at each time, we can label a record with a region and an event, and then merge those consecutive records having the same regions and event labels. An advantage is that the merging can be performed at a different spatial granularity. But this idea also poses challenges. First, positioning data obtained by wireless techniques often suffers from high positioning errors and a low sampling rate. Such spatial and temporal uncertainty make it hard to identify an object's exact whereabouts and mobility states. Second, indoor venues usually have small extent but complex topology. Existing annotation techniques for outdoors make use of POI category or human activity regularity, but they are incapable since the same type of POI is often placed together and object movement are quite random in indoor space. Third, an object's underlying regions and events are always correlated such that an object labeled as state within a time interval should not appear in multiple regions during that time interval. So such correlations over the sequence clearly increase the complexity of labeling. To address these challenges, we have the following technical contributions. First, we designed a novel graphic model, the coupled conditional Markov net, to capture the joint relationships among position records, region labels, and event labels. As probabilistic modeling is used, the spatial temporal uncertainties can be well handled. Second, we analyze the characteristics of indoor topology and the indoor mobility behaviors, and reflect those knowledges by designing a set of feature functions in our model. Third, to mitigate the coupling of regions and event labels, we devised an alternate learning paradigm that allows to alternately estimate parameters for one label type, with the other ones being fixed. We give the problem definition. A positioning sequence is a time-ordered array of positioning records, each consisting of a location and a time step. Then we define an M semantics as the triplet, in which R is a region, tau is a time interval, and E is a mobility event that can either be a state or a path. Then the M semantics sequence is also a time-ordered array. Our problem is to generate the most likely M semantics sequence for an object, given its positioning sequence. So technically, we can regard this as a sequence labeling problem that decodes the optimal target variable Y to maximize the conditional distribution over the observation X. We briefly introduced the conditional Markov net. In a CMN, the conditional distribution is factorized as a product of clique potentials. A clique is a full connected subgraph, and its potential can be regarded as an energy function, measuring the compatibilities among the nodes in a clique. The larger the potential values, the more likely the value configuration for the node. To facilitate the optimization, we use log linear combination of feature functions to represent a potential. Here, omega is a weight parameter and zx is a positional functions. For normalization, the sums of possible value configuration of x. So we further introduce the unrolled CMN for sequence labeling. When a net is unrolled over time, thousands of nodes may be involved and the net becomes rather complex. This makes it hard to compute the conditional distribution. So we introduce the parameter sharding that is for the cliques having the same relational structure. We treat them as coming from the same template, and we use the same parameter for a template. So this significantly reduces the number of parameters to estimate. On top of CMN, we present our design C2MN for mobility semantic annotations. In this net, each positioning record is an observed node. We linked it to a region label and also an event label. We unload this structure over time. In C2MN, we identified 4 categories of links. First, at each particular time, we treat each observed node and a target node as a matching click to measure their fitness. So for example, theta1 and R1 and also theta1 and E1. So second, we use the transition link to measure the label smoothness of two consecutive target nodes, like from E1 to E2 and from R4 to R5. Third, we design a synchronization link to measure the transition consistence for two pairs of an observed node and a target node. For example, the transition from theta2 to theta3 and from R2 to R3. So those two transitions should be consistent. The last one is a segmentation link. Suppose that R3, R4, and R5, they have the same label, and then they form a segment of the sequence. So we can put theta3 to theta5 and E3 to E5 in a link. So to see if these nodes are comparable to the region labels of this segment. So next, we explain our specific feature function design. Each function is used to extract some feature values to evaluate the labeling plausibilities of the node in a click. So then we put all feature functions in the log linear form, and the framework chooses the label configuration with the highest overall evaluation. Note that each function is associated with a weight, and this weight is learned from the training data. In total, we have functions to measure the plausibilities in 8 different aspects. So we just briefly introduced the basic idea of feature functions. So for more detail, please refer to our paper. The first one is called spatial matching functions between a positioning record and a region. So it computes the intersection ratio of the positioning records on certain area with the semantic region. So for example, both RA and RB could be the possible region label of L1, but in these functions, RB is more possible because it has a larger intersection area. So next, we turn to the spatial consistent functions, which considers the difference of the distance at the region level, and from Ri to Ri plus 1, and the distance at the location level from theta1 to theta1 plus theta I to theta I plus 1. So see this example. So for L1 and L2, we can label the regions as RB and RC. And the possible path is like the blue line. And then, but considering the uncertainties, another possibility is to label the two regions as RA and RD. So then a possible path is like the red line. So within a fixed elapsed time, we can say that the labels of RB, RC should be more normal. And the red lines possibly happens in some mismatching case caused by positioning uncertainty. So here are two segmentation functions. Note that they can only be identified when one target variable is configured. We take the event-based segmentation function as example. So if R4 to R9 have been configured as state, then for this state segment, it's more possible to have less distinct regions, less moving distance, but more turnings as the object stays around a small area. So these features are distinguishable. So here L4 and L7 are better to be in RG with the other records, but they are more like the noise now. So next, we introduce how to learn the weights with the fully labeled data. So here we use parameter sharing, that is each function above corresponding to only one weight vector, the omega ct. So we write the loss as negative log likelihood and use a zero mean Gaussian hierarchy to avoid overfitting, then the problem is to compute the partitioning function, as it needs to consider all possible configurations for R and E. To address this, we use an assumption that a node is only related to its immediate neighbors, termed as Markov blankets. So this so-called pseudo-likelihood simplifies the dependencies of variables, and we can still use iterative learnings to retain the relations among those non-labeling nodes. The optimization is done by Kawai's Newton method LBFGS, which requires both pseudo-likelihood and its gradients. We derive them as below. Here, Y is either a region node or an event node, and we only consider the Markov blankets for easy computing. For the expectation term, we use MCMC samplings to compute it. However, even doing this, we have a problem that E and R are correlated. If we want to configure a region node, we must consider the effect from its neighboring event nodes. And what's wise? To address this, we devise an alternate learning paradigm. In particular, we fixed the region sequence with some initial values and learn the parameters for event sequence. When a variable is fixed, we can do MCMC sampling with the current parameters. And after we update the parameters, we exchange the ordering of R and E and back to the loop again. So the iteration stops until parameters relevant to both R and E are convergent. So for experiments, we introduce several state-of-the-art and also C2MN variants that remove some particular clicks. For performance metrics, we have the accuracy of the region for events, and they have combined one. We also have the perfect accuracy, meaning both labels should be corrected. We use 1 month's Wi-Fi positioning data corrected from a shopping mall. The training data is obtained by our toolkit chips with a visualization function as shown here. So we did the tenfold cross-validation. For the results, we see our proposed joint labeling significantly outperforms those two-way methods that annotate regions and events independently, and the two-step method that annotated them sequentially. Also, a complete structure can get the best result. We also show that for the learning, configuring the event label first is more efficient. So as a summary, for semantic annotation of indoor position data, we propose C2MN to capture joint dependency among different nodes. We designed a set of feature functions related to the inner topology and the mobility behaviors. We devised an alternate learning paradigm to enable parameter estimation over the coupling of regions and events. Several future directions exist, like introduce more diverse events, extend to outdoor scenarios, and integrate with NER techniques. So that's all. Thank you.
Thanks, Antoine, for the great presentation. Again, we have a couple of minutes for questions from the audience. If anybody has a question, please unmute yourself and direct your question directly to Juan. Juan, I actually a couple of questions. Maybe we can take some of them offline. It's a very interesting work, and one of the questions that I have is the use of Markov blanket for optimization or for basically making and simplifying the dependencies. Have you evaluated the impact of the use of Markov blanket on the final accuracies? And your accuracies are great, but I was wondering whether you had looked at how much accuracy cost that simplification is bringing to your final accuracies.
Thank you. Thank you for the question. Actually, for this Markov blankets, we have not implemented this ones without considering this pseudo likelihood, because this involves a lot of the nodes in this in this learning. So the basic idea is we try this is like we think this this dependencies between the non-labeling nodes could be iteratively learned based on this kind of method. So we haven't tried that ways without this pseudo likelihood.
Okay, no, that's fine. That's great. My second question is, so your motivation is basically the outdoor settings, right? And then indoor settings, right? And for the outdoor settings, you said that they are simplifying, usually there are some simplifying assumptions made, such as regularity of the paths and the point of interest. But this may not be the case basically for indoor sort of sessions, indoor troubles, and I can kind of see that. So what would be, what type of extensions, right, so would it be required, right? So to take your research, right, and apply to some outdoor problem?
Yes.
Would it be directly applicable, or would you need to basically make significant change? Because there are parallels, although there are differences, there are also parallels between the indoor problem and the outdoor problem.
Yes, so actually for this outdoors, we have more informations, additional informations, like you have this category informations of the POIs. You have this, human may have some regularities, or they have some periodicalities to visit some POIs. Sure. So if you got such kind of informations, you can integrate them into some feature function design, and this could be helpful. And is actually we think this could be a good directions to extend to this outdoor setting.
All right. Okay. Yeah. Thanks a lot. Yeah. I can kind of see the extensions of your work to outdoor, and I'm glad that you are already thinking about that. Any other questions from the audience? Okay, if there are no other questions, then I would like to go ahead and thank Juan, and I would like to also thank all the speakers and all the audience for your attentions. Once again, this was the last technical session of today as well as of the conference, but please don't forget that there are still demos and posters that are running asynchronously, right? And also tomorrow there is a Women in Data Science Day that will go from 9 a.m. to 6 p.m. Local time. I encourage everybody to participate also in that event. Again, I think otherwise this is the end. Thank you, everybody. Thanks a lot. Thank you, Juan, once again.
Thank you.
Bye.